Hello again, scholars. This is Miss Gardner, and I am going to take you through a Unit 5 review over molecular geometry, polarity, and intermolecular forces. So this was a longer unit of the ones we've done this quarter, so this is a slightly longer video than some of the previous ones. All right, let's get started. So the things we're going to talk about in Unit 5 are what is an electron domain? How do the number of electron domains determine the molecular geometry of a molecule? What is a polar bond? How can we figure out if a molecule is polar? And how does polarity affect intermolecular forces? All right, so let's start here with molecular geometry VSEPR 101. Electrons. So electrons are what make up bonds, right? We have an ionic bond or a covalent bond, and that is between electrons. Electrons repel each other. So electrons have a negative charge. So if you have two of them in close proximity, they want to be spread apart, right? Opposite charges are attractive, like charges repel. So regions of electrons, also known as electron domains, will spread as far apart from each other as they can. So they just want to get as much room apart from each other so that their charges have plenty of space. So because they spread out, this causes molecules to have a three-dimensional shape. So they don't lie flat the way that we draw them on our paper. They actually take up space in all three dimensions. So this theory is called VSEPR, or valence shell electron pair repulsion, and it's the basis for molecular geometry and everything else we're going to talk about. Okay, so electron domains, that's where we're going to start here. So again, an electron domain is just a region where electrons are found. So let's look at our first molecule on the left, NH3. So how many electron domains do you see around the central atom? Well, I see one here, 2, 3, and 4. So all of these are electron domains. This has a total of 4 electron domains. 3 of them are bonding domains, meaning they're involved in a bond, and 1 of them is non-bonding. But so we still count those each as one domain, 4 total domains. All right, let's take a look over on the right at CO2. Again, we're going to look at the central atom, carbon, and I see 1 electron domain and 2. So remember, domains are just regions where electrons are found, so I'm not counting individual bonds or electrons. So we have 2 total electron domains here. They're both bonding domains. So the number of domains for CO2, 2, is going to give it a very different shape than the 4 electron domains in NH3. So when we're considering domains, we should only be considering the central atom. So just remember that we're only asking about things around the central atom. So let's test this out. How many electron domains are there around the central atom? So for A, we have BCl3. So look at your central atom and count how many electron domains there are. All right, letter B. H2O, or water. Look at that central atom and count how many electron domains are around oxygen. And letter C, this is ozone, or O3. Look at the central oxygen and tell me how many electron domains are there around here. Remember, we're not counting number of bonds or individual electrons, just regions of electrons. So the number of these electron domains determines the molecular geometry of a molecule. So let's reference this table. This is table 9.2, and I'm sure it looks familiar because we used it a lot in class. So let's start here. If we have 2 electron domains, that is going to force us into the electron domain geometry of a linear molecule. So if I have just 2 electron domains, if they want to be as far apart as they possibly can, the most spread out they can be is 180 degrees apart, or just at 2 opposite ends. So for these, they're all going to have 2 bonding domains. None of them are going to be non-bonding. and they're going to have a linear molecular geometry. So an example, like we just saw, is CO2. So here carbon, it's got two electron domains around it. The furthest apart that they can be from each other is just spread straight across. So that's going to be a 180-degree bond angle. If we have a molecule that has three electron domains, it's going to fall into the trigonal planar category. So now we've added in another electron domain. It wants to spread out as much as it can, but now there's three regions to spread out from. So we can have three bonding domains and zero non-bonding domains, like in the case here, BF3. And for those to spread out at a maximum distance from each other, they're going to have a 120-degree bond angle. That's going to be a nice flat shape. It doesn't have to bend at all in any way. That will be the maximum distance. If we have three electron domains, but two of them are bonding and one is non-bonding, that's going to take a slightly different shape. It's going to be a bent trigonal planar. And why is this? Well, notice this big kind of balloon here. The lone pair or non-bonding domain, so here is NO2 for this example, those actually take up more space than electrons in a bond. So this little balloon here is going to squish these two electron domains a little closer to each other. So now the bond angle is going to be slightly less than 120, so just a little bit shy of our trigonal planar here. All right, so we can also have four electron domains around an element. So if we have four, that will fall into the tetrahedral category. And if we have four bonding domains, they're all bonding, none of them are non-bonding, that will have a tetrahedral molecular geometry. So this would be an example like CH4. All right, so it's got four hydrogens coming out of that central carbon. And a maximum distance for these to all be separated from each other is going to be 109.5 degrees. That's going to be the optimum spread out nature that those electron domains could be. We can also have a situation where we have three bonding domains and one non-bonding domain. And it's going to be really similar, but remember that non-bonding domain, it takes up a little bit more space. So now these other bonding domains are going to squish a little bit closer to each other. You can think of that as like a umbrella that's blown the wrong way, right? Like it's crumpling towards itself. This is called trigonal pyramidal. An example would be NH3. So here I have my three hydrogens, so 1, 2, 3 bonding domains, and my one non-bonding domain up top. So since that takes up a little more space, it's going to be slightly less than 109 degrees. And the last type that we can have would be a molecule that has two bonding domains and two non-bonding domains. So an example for this would be H2O, or water. So here oxygen, it's got non-bonding here, the red unpaired electrons here, and then the two bonding domains towards the hydrogens. So since those non-bonding domains take up more space, it's again going to have a slightly less than 109.5 degree bond angle. Okay, so now quiz yourself using what we just reviewed. So letter A, so we have silicon tetrahydride, or SiH4. Count how many bonding domains we have, how many non-bonding, and figure out the molecular geometry. All right, let's look at letter B. We have PCl3. Count your total electron domains, your bonding and your non-bonding, and remember this is just around the central atom, and figure out the molecular geometry. All right, and letter C, we have CO2. We've seen this one already. Look at how many bonding domains are on the central C, and figure out the molecular geometry. All right, let's also consider polarity. So polarity is a difference in electrical charge between two ends of a molecule. So we first examined this through a comic that represented different atoms in a molecule as polar bears and penguins, and I think it's still a pretty good analogy. So let's consider electronegativity. So before we can really consider polarity, we have to understand electronegativity. So that is just the ability of an atom in a bond to attract electrons towards itself. So in our example here, chlorine, a very electronegative element, is represented by a large, strong polar bear. Hydrogen, not very electronegative, is represented by a smaller penguin here, and the electrons of the bond in between them is represented by 2 scoops of ice cream. So, since chlorine is more electronegative than hydrogen, the polar bear is getting more of the ice cream, right? It's pulling more of the electrons over towards its end. So because of that, chlorine feels a little bit more negative and hydrogen feels a little bit more positive. So this difference in electronegativity between the two elements causes the bond between them to be polar. So electronegativity follows certain trends on the periodic table. So in this picture here, we've got a little floating piece of ice. We've got polar bears congregated over here towards where our non-metals are. Penguins over here in the metals section. So our electronegativity values increase as we go left to right. With fluorine, or that would be this polar bear sitting in the high right corner, that would be the most electronegative element. And on the other end, this teeny little penguin down here is going to represent francium. So that's our least electronegative element. And notice here, no one's sitting here over where the noble gases are. So they're not assigned electronegativity values. And that's because they don't really attract electrons towards themselves because they don't form bonds with anything else. They already have that filled octet. They're energetically stable and they're not going to pull or push anything towards them. Okay, so we can also talk about electronegativity in a quantitative way. So we are going to look at electronegativity values, which you can see in this table here. So here fluorine has the largest value of 4.0, francium down here 0.7. All right, so they increase left to right and then they decrease as we go down. So if we wanted to put a number on it, a polar bond is just a bond where the difference in electronegativity values is greater than 0.5. And to calculate delta En, delta just means the change in, just take the larger electronegativity value and subtract the smaller. So it's always going to be larger minus smaller. It doesn't matter what order the elements are written. It's always a positive value. All right, so let's do some practice problems. So what is the delta En for a nitrogen-fluorine bond? All right, so I just need to go over here, find nitrogen, 3.0, fluorine, 4.0. All right, and then I'll calculate. Delta En will be 4.0 minus 3.0. Notice I do the larger value first, so it's going to be 4 minus 3 and give me 1. So according to our definition, is this bond polar? Well, yes, it's greater than 0.5. So a nitrogen-fluorine bond would be a polar bond. All right, you try a couple. So determine if these bonds are polar. Remember, 0.05 or greater, it's going to be polar. So a phosphorus sulfide bond. All right, take a moment, find phosphorus, find sulfide, subtract the smaller number from the larger number. All right, so you should have seen that the phosphorus sulfide bond is non-polar. That will have an electronegativity difference of 0.4, so that's less than 0.5. All right, let's do number 2, CCl. So need to find carbon and chlorine. 2.5, 3.0. All right, this one is a little tricky. It's right on the line. So we're going to have an electronegativity difference of 0.5, but we can go ahead and say that that's polar. All right, so that was just talking about the bonds themselves between two atoms, but a molecule altogether can also be polar. So for a molecule to be polar, it needs to have polar bonds and also be asymmetrical. Well, we know what it means to have polar bonds, right? That's just an electronegativity difference of greater than 0.5. But what about being asymmetrical? What does that look like? Well, a molecule, it can have polar bonds, but it can also be nonpolar. How is that possible? Let's think about that. Well, it's because it's a symmetrical molecule. So this is where now molecular geometry comes in, as we must consider if something is going to be polar. So let's take, for example, carbon tetrachloride. So we saw that that carbon chloride bond, even though it was right at 0.5, I said that was polar. So those are all polar bonds. But why is this molecule not polar? Well, it's totally symmetrical. So I've drawn in the direction of the dipole. The dipole is just a polar bond. So the chlorine molecule, that's my big polar bear. It's pulling electrons towards it, away from carbon. But they're all pulling in equal strengths, and they're all pulling opposite each other. So since this is a perfectly symmetrical molecule, all of those dipoles cancel out. So it's like basically you have tug of war with 4 equally matched polar bears, and the carbon doesn't move. And just a reminder that polar bonds and molecules are sometimes called dipoles. Okay, so what are some examples of symmetrical molecules? Well, here's BH3, that's a trigonal planar molecule. That would be something that's symmetrical. We have CO2, a linear molecule. CH4, a tetrahedral molecule with all the exterior atoms are the same type. O2, all right, that one, there's not really a central atom here, but it's symmetrical. Or carbon tetrachloride. So again, all of my exterior atoms are the same type, equal strengths tugging out. So let's look at some asymmetrical molecules. NH3, all right, so notice here I have this region up top where I don't have a hydrogen here. So now all of the dipoles, whereas if there was a hydrogen here, that would cancel it out. They're now all pointing towards nitrogen because nitrogen is more electronegative than hydrogen. All right, SO2. So let's think about the molecular geometry here. How many electron domains do we have? See, 1, 2, and 3. But there are 2 bonding domains and 1 non-bonding. So this is a trigonal planar bent geometry. All right, so many times our bent geometries are going to be asymmetrical. Here's SH2. That's another bent geometry there, more of the tetrahedral category. Here we have NF3, so another tetrahedral, but this is trigonal pyramidal molecular geometry. HCN, well, this is a linear molecule, but why is this asymmetrical? Well, the exterior atoms are not the same. So I have a nitrogen here and a hydrogen here. So because of that asymmetry, this could be a polar molecule. And H2O. H2O is one of the most polar molecules, and it's going to lead us into our next topic. So the last part of Unit 5 was intermolecular forces. So an intermolecular force is a force between 2 molecules. So in our image here, we have 2 HCl molecules. The intermolecular force is the one felt between them. The one within the molecule, here a covalent bond, that is considered an intramolecular force. So we're thinking about intermolecular, or between molecules. So these forces are generally weaker than the forces within molecules, but they still can cause things to behave a certain way. So like I said previously, water, since it's asymmetrical, it's very, very polar. So if I draw the dipoles in, I'm going to draw it pointing towards the more electronegative element. So here, oxygen 3.5, hydrogen 2.1. So that's an electronegativity difference of 1.4. So my dipoles are going to point towards oxygen. And so oxygen is going to feel a partial negative charge, and hydrogens are going to feel a partial positive charge. It's like this unbalanced distribution of electrons. There are a couple different types of intermolecular forces that we learned about. The first one is ion-dipole. This one's pretty straightforward. It's just between an ion and a dipole. And here a dipole means the polar molecule. So here's our ion and our dipole. Ion, dipole. And the force itself, represented here by these dotted lines, it's the attractive forces between the partial negative end here of oxygen to the positive sodium, or the partial positive end of hydrogen towards the negative chlorine. All right, we can also have dipole-dipole forces, which is just between two dipoles. So special case that we talk about a lot is hydrogen bonding. So notice there's a lot of dipole-dipole forces happening between all of these H2O molecules, and they're all oriented so that their partial positive ends bump up against the partial negative ends of another molecule. All right, we can also have dipole-induced dipole. So this is when a polar molecule bumps into another molecule that's nonpolar, and it makes the nonpolar molecule feel a little polar. So say we have this nitrogen molecule, N2, just hanging out, and then a water molecule comes in and bumps into it, another one comes in and bumps into it, and it suddenly feels a little unbalanced. It's going to happen really quickly, but that is a dipole-induced dipole. We also have London dispersion forces, also known as LDF. So these are always present. And basically molecules, because there's a little bit of temperature, no matter where you are, a little bit of heat, the molecules are always wiggling around a little bit. So they're bumping into each other and they're causing tiny little dipole moments. So take a moment and look at this image here. What three intermolecular forces are present? All right, and the last part that this leads us into is solubility. And I've summarized this very quickly. But the main thing with solubility is that like dissolves like. So polar molecules dissolve polar molecules, and nonpolar molecules dissolve nonpolar molecules. So in this example here, we've got water, the clear liquid, and oil, the yellow liquid. They don't mix. Water is polar, it's attracted towards itself. Oil is nonpolar, so water is not attracted to that. So all the water molecules are going to hug up tight and close to each other and ignore the nonpolar molecules, and they're not ever going to mix. The only way that they would mix is if we had something called an emulsifier. So that's something with a polar and a nonpolar end, and it kind of acts as the go-between. So that's how soap works. Okay, I hope that this video helped you remember some of the topics in Unit 5, so you can use this or your previous notes to help you complete the Kahoot. All right, have a good day, scholars.